Welcome back to another video, everybody. I am sorry I haven't been able to upload in 3 weeks. I had some technical difficulties with my computer for a couple weeks, and then I was gone on family vacation for another week. But I am back and ready to make some more videos for you all. Today, we're going to be talking about U-substitution and integration. Now, a lot of the times, it's not that hard to understand how to do it, but why does it work and what is it? And that's why I'm here. To begin, let's talk about U-substitution in a place that isn't integral calculus, because it might be a better place to start anywhere but that. Consider a quadratic. X to the fourth plus 5x squared plus 6 equals 0. Wait a second, this isn't a quadratic. A quadratic is a second degree polynomial, but this is clearly a fourth degree polynomial, so what's going on here? Well, here's the thing. This is still a quadratic, but we can't think of it in terms of x. We make a substitution. We'll let u equal x squared. Now we see that this equation becomes this equation, u squared plus 5u plus 6 equals 0. Now that is a very nice quadratic. We can use factoring and we can find the values of u, and then we can plug those values of u into here to find the correct values of x. Now let's talk about it in a sense that's more closely related to integration by discussing the graphs of certain functions and then applying a U-substitution and what would that resulting graph look like. In a similar case, we're going to use a U-substitution as u equals x squared. But now let's consider the two graphs. For y is equal to x squared, if this axis is x, and of course this is y, then we get this parabola shape, right? But if this is the u-axis and this is y, then we get a straight line. So how come that works out like that? I mean, if y equals x squared and y equals u and u equals x squared, then these two should be the same thing. So why do they look so different? Well, the answer lies in the fact that these are two different worlds, right? This is the y-axis in both cases, but the x-axis and the u-axis contribute to two different graphs because this is y in the x world and this is y in the u world. We discuss these as two separate worlds, essentially, is the way I like to think of it. And this relationship tells you how to go from one world to another, but if you can work in one world, that's a lot easier. A straight line is a lot easier to manage than a parabola in a lot of cases. Then you can work in the u world and then translate it through this back into the x world. So now let's bring that idea into the relevant sphere. We're going to be discussing U-substitution in an integral, finally, right? Now, the first step is to figure out what we want the translation factor to be between u and x. Now, looking at this integral here, what we could do is we could multiply this out to be x plus 3 times x plus 3 times x plus 3 7 times and do the multiplication, and you could, from there, do the power rule a whole bunch of times, and you would get the right answer technically, but that sucks really bad. Why would you do that when you could just use a U-substitution? For this case, we want the inside to just be a neat variable, because if it was, instead of x plus 3, if it was just x to the 7, we can just do a power rule. That's nice and easy. So what we'll do is we'll imagine a variable, a nice variable, be equal to that inside, all right? Now, if u equals x plus 3, well, what does that get us? It doesn't really matter, right? I mean, we're integrating with respect to x. Right now, we're in the x world. So let's bring the integral into the u world. To do this, we'll be using this relationship that we have here and take the derivative on both sides with respect to x. On the left side, we'll just get du dx, and on the right side, the derivative of 3 is just 0, so that goes away. And then the derivative of x is just 1. So we get du dx equals 1. Now what this means is that du actually equals dx. Every infinitely small chunk of x will be the exact same size in the u world. Now this makes sense because if u is equal to x plus 3, then that's only a vertical shift and it shouldn't affect the horizontal slice at all. Now from here, what we can do is we can replace this dx with a du. And then this x plus 3 is a u because u equals x plus 3. So we have this new integral of u to the 7th du. Now this is a much nicer integral to look at because we know how to do this already. I talked about this in the last video. It's going to be the reverse power rule. This is going to be, you add 1 to the power, so 7 plus 1 becomes 8, and you divide that in the front. So we get 1/8 u, and then that power stays as 8. But we're not done because we need plus c, since it's an indefinite integral. So this is the full process, but we can't box our answer yet because our original integral was in the x world, and this is in the u world. Now, like I was saying earlier, we can translate back from the u world into the x world by just using that factor that we had before, that u substitution. If u equals x plus 3, then we can go the other way. The u here becomes an x plus 3 here, and we have 1/8 x plus 3 to the 8th plus c, and that is our final answer for the integral. Now, there are a lot more cases of u substitution, and I will probably be going over those in a later video. But for now, this is just the introduction to the concept. Hopefully it makes sense. Hopefully you understand it. Hopefully you appreciate it. And thank you so much for watching.